Okay, good evening. Let me start from where we stopped yesterday. We were talking about uh, the field effect transistor, which is short form is called as FET, which is one of the most important electronic device, semiconductor device, similar to transistor. And also we saw about SCR. And we saw the basic function of a FET, which is nothing but by controlling the voltage at the gate, correct? We say we supply a voltage in the gate, which is a VGS. That means we say that this is common source FET amplifier, correct? Instead of using transistor, we are using field effect transistor as a electronic device to amplify the input signal. What is input signal? The voltage applied at the gate. In case of transistor, we are applying base current, correct? This is base current is input, output was collector current. This is input, output was collector current. That is the output. We know that. Then beta is called the current amplification factor. Current amplification factor. That means IC is related to base current by beta times. Beta is called current gauge. That means if I give some X amount of current in the base, it will be multiplied by beta times and it will produces output at the collector. The collector current, we know that already, we know that we connect our, for understanding purpose, again repeat, even though we studied previous one, this is what our common emitter configuration transistor based amplifier. We know that plus minus, this is called VCC, and we give one more voltage called as VBB, that is called base voltage. This is plus minus. This is NPN transistor. I know that emitter is coming here. This is collector, emitter. This is base. This is called RB, base resistance. This is called as RC, also called as RL. We know why. The RC or RL is nothing but load resistor. That means we want to drive some electronic or electrical device load. For example, the RC can be a bulb, correct? I wanted to control, this is the bulb resistance. A bulb, electrical bulb connected to the collector, and that is given to plus VCC. So this is my bulb. Bulb has resistance, correct? We say the bulb resistance, I say RB, bulb, correct? So that is nothing but your RC. Now the current from this will flow through the IC and end up in, there's no space. Let me clear this. So we'll cross here itself. I can show it because there's a limited space. Let me show it here. So here, this is my bulb. I can say the bulb coil. Okay. So that means if current, this is my IC. IC is nothing but IL, load. This is my called as load resistor. RC is nothing but load resistor. I can connect, it can be a motor, any electrical device which I wanted to drive using this transistor. I will connect it to between power supply plus VCC plus and collector. So if I control the base current IB by controlling the VB 0 to 5 volts, RB is the resistance, I say the 1000 ohms. So if I vary 0 to 5 milliamps current will go. IB will vary from 0 to 5 milliamps. If I say my beta equal to 100, beta of the transistor, IC will be 0 to 500 milliamps. So we know that my transistor is amplifying my input current, which is nothing but base current, 100 times. So that's why we call it amplifier. Similar to this, in case of FET. In case of FET, let me erase all those things. You understood many times, I repeated, but I know that you will get better clarification. That's why I mean, many of you are mechanical students. So few of maybe electrical electronics. So to make you to understand, clarify, and have deep understanding, long-term store it in long-term memory, so that I'm repeating this. But in case of similar to this, I have my N channel. This is called N channel FET. Already I told you N channel FET means we take a bar or a cylindrical bar of N type material on which we dope the P type material. Again, for the understanding purpose, showing this is P type material, which is nothing but both sides. This is called as a channel through which the current IDS, which is similar to ICC. This is my VDS plus minus, and this is my gate voltage plus minus, and I can vary this voltage. Please note that depending upon whether N type or P type, the gate voltage can be minus plus, right? If it is to control the current IDS, I should change the bias voltage applied to gate, which is called a VGS with respect to source, whether it is N channel. If it is N channel, again, for you understand quickly, I will draw. So this is N channel MOSFET. P channel MOSFET means the bulk material or the main material will be made of P type material. This is P material. So that means it has positive charges, which is called as hole everywhere. Please note that it is everywhere. And this I deposit this one contact is called as a drain. Between this and other contact is called as source. Other end, source terminal called S. This is called a D. And we supply the VDSS minus plus. Correct? This is VDS in case of P channel. Okay. Then, so this is bulk material is P material. Everywhere you have positive holes. And we are biasing with negative voltage applied to the drain and this one positive applied to source. Then what we do is, this is my N material. That means electrons are there, N type material. And I deposit metal contact on both sides. And these two are called as gate. Correct? Gate, both sides. Again, you can see that exactly similar to this is N channel. Correct? In N channel, the channel is this region through which the current from the supply is flowing through like this. And the width of the channel, as I told you yesterday, the width of the channel, whether it is small, make it small or make it big. Correct? You can vary, but maximum is this. Already this is the maximum. From this, you can reduce this width. Correct? Channel width can be reduced or increased by varying the gate voltage, VGS. VGS is varied from 0 to minus 5 volts. We saw that 0 to minus 4 for in case of N channel, or this one P channel reverse. So again, here you will apply a voltage with respect to source. Okay. So you can see that this is my channel. What is this material? P material. That's why they call P channel material. Again, source. This is source. This is control voltage. Correct? This is control voltage. Due to this, what is the output? IDS. IDS is the current. So input in case of FET equal to VGS. Voltage applied between gate and source. Output is nothing but IDS. That is current flowing between the drain and the source. Whether it is a P channel or N channel, this. And by varying the input, this one, that's what we show you. I showed the graph also. Correct? This graph is, we are trying to control the base current. Sorry, gate current, gate voltage. Extremely sorry, gate voltage. We are applying the gate voltage. And so, because of this, as I told you yesterday or not, that FET is, note down, FET is called as voltage control device. Why? I vary the VGS, which is VGS is varied as input. Because of that, IDS is varying as output. Correct? Input voltage is controlling output current. That's why FET is called as voltage control device. But in case, if you see, in case of transistor, input is IB, base current. Output also is IC, base current, or they call collector current. So transistor is called as current control device. It's called a current control device. So, okay, you may ask, having a current control device like transistor or a voltage control device called as FET, right? So, anybody remembers loading effect? When we talk about mechatronics, we were talking about loading effect.
So even
in case of sensors.
Right?
In case of sensors, loading effect should be avoided. We talked about loading effect. Somebody told. Can you repeat? Loading effect, somebody told now.
Sir,
yeah.
It's basically the offset we are going to get during the reading of the value, right? Something like that.
Yeah, change. This is error. It is not, you are correct, but the wording should be. See, for example, if you take a thermocouple, that's what we are talking. TC.
Seebeck effect and thermocouple.
Yeah. Now I am giving heat energy. Heat energy as an input, right? Q. Because of that, there's a temperature T. T where is heat energy? I give 0 to 1000 joules. Correct? I have supplied, and because of that, the junction is getting temperature 0 to 100 degree for understanding purpose. So, what is the output of thermocouple? EMF. It will vary 0 to 10 millivolts. That's what we said. Okay. This is called a open circuit voltage. It is called as open circuit voltage. Now, if I connect this, because you know that the voltage is in the order of 0 to 10 millivolts only. This voltage cannot be directly used for controller, because the sensor voltage should be given to the controller. Controller will generate proportional control say given to an actuator. Actuator can be electric motor or engine, something like that. We know that we have a sensor. Sensor output is given to controller. Controller output is given to actuator. Correct? So this is electronic controller. It can be digital controller or another controller, op-amps. Correct? Already it's an op-amp based amplifier, integrated, different, all those things are there. Or micro going to write the program. Correct? So this is my temperature sensor. Correct? TC. And if here it is going to sense the temperature on an object. Object is this one. Input is given as a Q, heat energy, because of the temperature. I have metal block. It is getting heated. I wanted to measure what is the temperature. My thermocouple touching this, it produces 0 to, for example, 50 millivolts, and get 0 to 500 degrees centigrade. That is what the output is coming here, but it is in millivolts. If I directly give to controller need higher voltage. We need 0 to 5 volts, because my sensor cannot give higher current. Correct? It can produce millivolts. If I try to connect to a load, we know that there will be a current flow. I say sensor current. I connect it to one controller. Controller takes some current. Controller takes some current from the sensor. Because of that, for example, if temperature I told you is 50 degrees centigrade here, and it gives 5 millivolts, and on open circuit, once I connect it to the controller takes some current. Current start flowing. In open circuit, there's no current flow. But once I connect to controller takes some current, which is called input current. Correct? If controller takes more current, the voltage, because if the temperature is 50 degrees centigrade, the thermocouple was giving 5 millivolts. But thermocouple cannot supply current. For example, this controller takes 10 milliamps current. Please note that you may think 10 milliamps is very small current. But as per thermocouple is concerned, if I draw thermocouple 10 milliamps current, while it is producing 5 millivolts, when temperature is 50 degree, the voltage will reduce to, for example, 4 millivolts or 3 millivolts. If I connect to controller, because controller is taking current from the sensor, that is called as loading effect. Any controller or electronic device which is connected to sensor takes current from the sensor, because please note that all the sensor produces voltage proportional to input parameter. Being a temperature sensor, thermocouple 0 to 100 degree, 0 to sorry, instead of force transducer, we know the strain gauge based force transducer. We use Wheatstone bit. It use what is that? Strain gauge, correct? 4-arm strain gauge, half-arm this one. So there also give, if you try to take current from the this strain gauge bit, then the voltage produced will become less. If basically what is loading effect? Taking current, note down, taking current from the sensor by any electronic circuit, control circuit, all those things. Sensor is just gives a parameter. It cannot do anything. That value should be given to some controller. Controller based on that will find out what is the temperature. Right? We know that thermocouple gives 0 to 10 millivolts when temperature varies to 0 to 100 degree, or 0 to 50 milliamps millivolts when temperature varies 0 to 500 degrees centigrade. So by seeing the voltage at the thermocouple sensor output, the controller knows what is the current temperature of the metal block or object, correct? Humidity, whatever it is. So now, based on that, the controller generates some control signal to switch on something. If temperature is this much, open the valve, close the valve, something like that, correct? So that is done by opening and closing is done by actuator. It can be a motor, solenoid, something. So that is controlled by controller, but input is coming from sensor. But the electronic, this controller, if it takes some current, it should, please note that controller should measure only the sensor output voltage. It should never take current. Correct? If it takes current, that is called a loading effect. If the controller takes some even small milliamps current from the sensor, when the temperature is 50 degrees centigrade, in open circuit, without connecting controller, thermocouple was giving 5 millivolts. That means 50 degree. Once I connect the controller, immediately the voltage drops to 4 millivolts or 3 millivolts or 4 millivolts lesser than. That means now we know that if it is 5 millivolts, the controller knows it is 50 degree. That is the correct temperature. But since the current is taken by the controller from the sensor voltage drops. That is called as loading effect. Correct? Because of that, now it becomes 4 millivolts because current is taken. What the controller thinks? The temperature of the metal block is 40 degree because 4 millivolts represent 40 degree. 3 millivolts represent 30 degree. Correct? 6 millivolts is 60 degree. Now, the temperature, even though the temperature measured by thermocouple of the metal block is 50 degree, because the sensor voltage was reduced due to loading everything, because the controller took some current. So literally I told you, theoretical controller should not take any current from the sensor. But that is theoretical. So the practical sensor will take milliamps, microamps, nanoamps, something like that, which cannot be avoided. Because of that, the actual temperature produced by sensor, which indicates what is the temperature, the wrong measurement is made by the controller. Controller thinks that because my thermocouple output is 4 millivolts, it is 40 degree. But actually, it is 50 degree. Why? The thermocouple produces 5 millivolt. When open circuit, once the control is connected, it took some current, so voltage drop reduces. Voltage reduces from the sensor output. That is called that is an error in measurement. If I wanted to reduce that, what I have to do? I should have a controller which will not take any current, which will not consume or take current from the sensor. Consume or take current from the sensor. That means the controller, that kind of controller is not there. So that's what I want to say. So, but one way I told you is to reduce the amount of current taken by the controller. Okay. That is one point. Next important point, what I want to say is in the sensor itself, because the FET amplifier, you will understand this one. If I connect a transistor, correct? So we know that my thermocouple is there. This is my TC thermocouple. It has plus minus, and here is a metal block, and it is getting heated. Q is the heat energy, and because of that, temperature is increasing 0 to 100 degree, depending upon how much heat energy you are supplying. Okay. Now I want to measure. So my thermocouple is touching the metal block. So because of that, it produces an output. So 0 to 10 millivolts. That's what we talk. Okay. This voltage, if I give directly my to controller, correct, to my controller, which is going to control a actuator. This is the controller, correct? Controller supply with supply Vs, and that is going to supply the current to the actuator, which can be a motor or a solenoid, correct? Solenoid is a load, anything. It can be electric motors, a heater, any electronic device, electrical device, which is going to drive your system, opening valve, closing valve, heating, something, whatever it may be. Okay, so this need an input, and which input is the current parameter. What parameter? This is a temperature control. The whole thing is a temperature controller. Temperature control system. Okay. So the controller measures and accordingly produces this one. So that means this is a heater. This heater is coupled here. Correct? I wanted to control the actually nothing but an electric heater, which I am supplying voltage. That should be controlled. Who is supplying voltage to heater? The electronic controller. Electronic controller is supplying voltage to actuator, which is nothing but a heater, electric heater. So this one, it is heating this metal block. Now I wanted to maintain some 50 degrees centigrade. Right? I can control anywhere between this by varying the heat temperature. So which is supplying heat. Now, if I directly give to controller, this, if I like this will take some current. Correct? So the controller will take some input current. At 50 degrees centigrade, if the temperature is 50 degrees centigrade, here it will be 5 millivolts. That is open condition. Now, if I connect the controller, you say, for example, 1 milliamps current is taking the controller. Okay. So because of that, this will become 4 millivolts. For example, understanding purpose, 4 millivolts. 4 millivolts means the controller thinks that already controller is programmed such that if input voltage, this voltage is varied from 0 to 10 millivolts, the controller is nothing but 0 to 100 degree centigrade of this metal block. That is how you have programmed. Correct? How the controller, what is temperature of this object? It measures the millivolts output coming from my thermocouple, which is my sensor. And if it is connected to this controller, the controller looks to what is input voltage. If it is 0 millivolts, it knows that this metal block is 0 degrees, it's not getting heated up. Like if it is 100 degrees centigrade, this will give 10 millivolts. 10 millivolts is saying that is zone. But that is all these things are called open circuit voltage. Open circuit voltage of the sensor. Okay, as long as I don't take current. Just sensor, I connect a multimeter, which measures 0 to 10 millivolts without connecting this one. Multimeter is correct. Multimeter is supposed to take 0 current. Theoretical multimeter also, but most of the multimeter take nanoamps peak or digital multimeter, correct? You have the digital. So they take micro to nanoamps, right? Few nanoamps, it can be considered close to 0 volts. That's why if I use digital multimeter across my thermocouple, loading effect will not be there. Digital multimeter, what you are using in the office, all those things, correct, is designed so that it takes 0 current, but still it measures what is the output voltage produced by the thermocouple without taking current. It is not taking without taking, it takes very, very, very small current. Instead of milliamps, it takes nanoamps, this one. Why I'm telling is the digital multimeter, correct? Also in input correct stage, it has a FET or MOSFET amplifier. That's why I'm talking all these things. They don't use transistor amplifier. They use FET or MOSFET amplifier. Because of that, it doesn't consume any current. Maybe in the order of microamps, nanoamps, which can be neglected. It can be considered as 0 milliamps current, correct? So we say that no loading effect. So now, to avoid this, we know that if I put a FET as a amplifier, FET amplifier, correct? So here I put a FET amplifier. Then the input is given to FET amplifier. After that, output of the FET amplifier is given to my controller. Okay. The output from this is given to my FET amplifier. This is the sensor. And from here, output is taken, amplified and given to. So my FET amplifier, being a voltage control device, what I said, voltage control. So that means I am supplying base, that is a gate voltage. This is gate, this is drain, this is source. I am supplying, this is my sensor, correct? Instead of the VGS is nothing but my sensor. Let me clear it, you will see it still better. Okay. What I will say is, this is not there. Instead of that, my thermocouple is connected. Correct? This is my thermocouple. It produces 0 to 10 millivolts. So this, since voltage is supplied instead of, because the FET doesn't take current. FET current does not consume much higher current. I can say, please note that theoretical FET supposed to take 0 milliamps, 0 current, but practical FET always takes in the order of microamps, nanoamps, correct? At least microamps, much current, generally consumed in the order of microamps, 10 power minus 6. Okay, because the FET doesn't consume, but the input current voltage coming from sensor is applied direct to gate. That means I am varying my VGS from 0 to, for example, 10 millivolts. Correct? That's what, when temperature varying 0 to 100 degrees centigrade, my thermocouple produces 0 to 10 millivolts. That is given as a VGS. My input voltage VGS is varying from 0 to 10 millivolts. This is my sensor input. And the FET doesn't take current. I told you theoretically it should take 0 current, but most of the FETs practically available may take in microamps, nanoamps, so it can be neglected. But if you connect the same, this one, my thermocouple to my transistor. For example, your transistor is connected like this, NPN transistor. This is my RB, this is my TC, this is IB. This is, for example, BC107. I told you many times we have talked to. So we given, say for example, 10 volts VCC. This is equal to 100 ohms. This is equal to 1 kilo ohms or 1000 ohms. Correct? Then what happens? This voltage is varying 0 to 10 millivolts. For example, if temperature is 50 degrees centigrade, what is my output? 5 millivolts. TC output is 5 milli. When the temperature 50 degree, correct? So 0 to 100 degree varies. The output will be 0 to 10 millivolts. Currently, the temperature of the object is 50 degrees. So my thermocouple output is 5 millivolts. Now, what is the current IB? This is my IB. My transistor gain of beta equal to 100. And this is this one. What is IB? IB equal to, we know that input voltage, TC voltage is 5 millivolt into 5 into 10 power minus 3. That is the input voltage. That thermocouple output is given as input to nothing but VB, correct? Divided by, this is 1000. Right? You can see that this is 1000. So I can say that 5 into 10 power minus 6 amps. IB equal to this much. So this is another 5 microamps. Okay. Please note that the current is very, very small. Okay. But still some amount of current is taken. Once I connect to my transistor amplifier, for example, for understanding purpose, because this two looks too small, I put RB equal to 100 ohms. for understanding purpose, I make it 10 ohms because many times many application happens. So that means this will be divided by 100. This will be 10 power minus 5, 50 microamps. So if 50 microamps current is taken by the as a base current by the transistor amplifier, what will happen? This 5 millivolts will be reduced to, for example, 4.9 millivolts. Okay, so 4.9. So the output what coming because of loading effect of the transistor, because transistor consumes base current because it's a current amplifier. That is amplify 100 times. So my IC will be 50 into 100 equal to 5000 microamps or 5 milliamps. That's my IC. So amplification happens, all those things happens. Okay, but that is no, because of this, there's a loading effect. Correct? Loading effect happens with there's an error. Please note that the input voltage will not be 5 millivolts, it is 4.9. Correct? So once I connect my transistor, my IB equal to 4.9 into 10 power minus 3 is nothing but millivolts divided by 100. Correct? So it is going to be 49 microamps. My IC equal to 49 into 100 equal to 4900 microamps or 4.9 milliamps. But please see that what is the output after amplification? Also, because of loading effect, the sensor voltage is reduced by small amount. This is called a loading effect. So that means if I use transistor amplifier, which is a current amplifier, right? Transistor amplifier is a current amplifier. Loading effect is there. Instead of that, I take my same thermocouple, connect it to my FET. Okay, here there will be resistor. I say RDS. This is VDS plus minus. This is N channel FET. N channel FET arrow is going in. This is my gate. This is my drain. This is source. N channel FET. Okay, connected like this. And I am connected. This is my TC same thermocouple plus minus. This is ground. Okay, so we are given here. What will happen? This is called VGS. Please note that IGS is nothing but current flowing into the gate and coming out. Like IB, this will be almost close to 0 amps or many times in the order of nanoamps, 10 power minus 9 amps, which can be called as 1 nanoamps. Because FET, why does FET has high input impedance? Note down, FET has high input impedance. Inside that, there's a resistance offered between gate and source that is called as very high. It will be in the order of 10, hundreds of, maybe 100 megohms or 50 megohms. Correct? Mega ohms. So that means 100 into 10 power 6 or 50 into 10 power 6 will be input impedance at least in the order of 5 to 10 megohms. Not this much, also at least in the order of megohms compared to the base to emitter resistance, which is in the order of kilo ohms. Okay, that's why it takes current. So FET has a high input impedance at gate terminal. Note down. Because of that, if I use a FET as an amplifier to amplify the signal from the sensor, any sensor, it can be thermocouple, it can be strain gauge bridge, or it can force transducer, or temperature, or the humidity transducer, whatever transducer, electronic transducer, whose output generally in the order of millivolts to sometimes even microvolts, depending upon this one, not in terms of volts. That has to be amplified. Sensor output needs to be amplified many times. Correct? For that, instead of using a transistor amplifier, if I use a transistor amplifier, it takes base current. You can say that the transistor input impedance is low. Low means we are talking in the order of kilo ohms. Correct? Kilo ohms. Maybe 100 kilo ohm, 50 kilo ohm, 10 kilo ohm, something like that. Because of that, if I give you input voltage, input current is going, IB is going. And because of that, the input voltage, sensor voltage reduces, which is not the true representative actual temperature measurement or force measurement. So that error is called loading effect. So loading effect comes if I try to amplify the sensor signal using transistor amplifier, which is in a current amplifier whose input impedance is low compared to FET. FET, as I told, mega ohms, 10 mega ohm, 5 mega ohm, 50 mega ohm, something like that. Okay. So the transistors in kilo ohms. Voltage divided by kilo ohms will take more current compared to same voltage divided by mega ohms. So that's why we are to they have invented FET amplifier. First invention was transistor. Subsequently, they invented FET. Then they invented MOSFET. Okay. So MOSFET is a better version. Okay. Now you understood what is the advantage of having FET amplifier. Any doubt? So what?
Sir, FET and JFET are same, na?
FET, yeah, correct name is junction field effect transistor. That is, many times people just say field effect transistor.
Okay,
Sorry.
thanks.
Similar to bipolar junction transistor, BJT is the correct name for bipolar junction transistor. That is the correct name for transistor. Many times telling the big name is difficult. Most of the time they just say transistor. Correct technical name is it has two junctions, base to emitter, emitter to collector. The two junctions is why bipolar junction transistor, BJT. That is the correct name. Similarly, this is also called junction field effect transistor. Junction field effect transistor. Because transistor is going to amplify. This is also transistor, but only thing is it is controlled by gate voltage. In case of regular transistor, base current. Here it is gate voltage. That is why advantage. So since it is not taking current, that's why we say base that is gate voltage is changed. By changing the base the gate voltage, the IDS drain current will be controlled, which is output. So that's why it called as voltage amplifier. And it is advantage. What is advantage? It avoids loading effect. Wherever you want, if you see, already we saw about the op-amp, right? Op-amp already we know. We saw that extensively. Nowadays we are using op-amp. Now op-amp can be made with transistors. Already internal circuit diagram showed, correct? UA741 I showed you. It has a differential amplifier. After that, many stages are transistors. Plus minus 2 input. This is my output. This is called as non-inverting input. This is called inverting input. I connect my sensor here, TC, and you give power supply plus VCC and minus, we say the VSS, correct? Minus VSS, supply voltage. And this is my output. This is my input terminal. We call V in plus and V in minus. What is the output? V naught equal to V in plus minus V in minus multiplied by AD. What you call it? AD is called as differential gain of op-amp. Correct? Already told you this op-amp is nothing but made of many transistors. What we saw, transistor amplifiers only. If there are op-amps available made with using transistor amplifiers internally. There may be 10 or 20 or 30 amplifiers connected. If internally inside the op-amp IC, for example, UA741. UA741 internally it uses a transistor only. Multi-stage transistor, already we saw that. So this already I told you that UA74 itself avoids the loading effect compared to just a single transistor. We saw the single transistor, common emitter transistor. Where is that? I deleted. Yeah, this if I use a single stage amplifier, transistor amplifier, it will consume some current from the sensor. There can be error because the voltage when I connect the amplifier, it takes current in this one. So there is a measurement error. They call loading effect. So to avoid that only, I told you they developed what you called as op-amp. Op-amp advantage, we already told you, it has very high input impedance. very high input impedance compared to the single transistor amplifier. It has very low output impedance. Output impedance, already we saw, most important. It has output impedance. That is important. So because it has very low input impedance compared to transistor, if I use op-amp itself, in which internally you may have transistor amplifier. In 741, there it has some 14 or 15 transistor connected multi-stage amplifier. And we know that the AD of, see, this is 10 power 6. Correct? So very high. We know that AD should be theoretically I want infinity. Already we know why, already we derivation also we did. Anybody remember? Feedback, negative feedback. If I giving negative feedback, what we made, my input impedance generally for this one, mu-A74 is close to 1 or 2 megohms. This is called as input impedance in terms of ohms is 10 power 6, 10 power 7. That is called open circuit. Open circuit input impedance. If I give negative feedback, correct? Once I give the negative, we call Zin. Zin is 10 power 6 in case of mu-A741. This is nothing but open circuit input impedance. This is a very high. This is much, much higher than the transistor amplifier, which will be in the 10 power 3 to 10 power 4 or 10 power 5 kilo ohms. This is megohms, much higher, at a 2 times better. Now, if I give negative feedback, what happened? Zin with feedback. Anybody remember? The negative feedback, if I give like this, sorry, this is minus, this is plus. If I give this is RF, this is Rin, and Zin is internal. ZF equal to, any idea? Zin multiplied by 1 plus AD. Okay. Already you know Zin equal 10 power 6. If my AD, I told you 10 power 6, 1 plus 10 power 6, it is going to be 10 power 6 plus 10 power 12. Correct? So this is negligible. You can say that it has increased twice. If I give negative feedback in op-amp, it will become high. So this is transistor based. There are op-amps, if I remember 749 or 748, exactly I don't remember, mu-A or something, it internally it has FET, not transistor. It is so his input impedance Zin open circuit will be 10 power 8 or 10 power 9. And it has gain of, for example, AD equal to 10 power 6. It will be 10 power 8 multiplied by 10 power 6 will be 10 power 14. So if you are going to use op-amp, operation amplifier, to amplify some sensors which are producing, for example, millivolt, microvolts, for example, deep space antennas, correct? For example, Mangalyaan is there, correct? Mangalyaan is sending measures, because we have sent Mangalyaan to Mars, correct? So it is something around billions of kilometers. From there, it measured temperature, all those things, sends to ISRO office in Bangalore through radio waves. So when you receive the sensor signal, it will be microvolts or nanovolts because traveling so much distance. That is big by the antenna, correct? That signal needs to be amplified. You cannot use even 741 op-amp with input impedance with feedback equal 10 power 12, correct? With the negative feedback. So in that case, what they use? FET input op-amps. Okay. Whose input impedance is in the order of 10 power 9 to 10 power 12 in open circuit. If I give a negative feedback, it will become very high. It won't consume any current. Loading effect is avoided. Correct? So that's okay. Let me. So because of that only, we can know that this FET has advantage. Okay, compared to transistor amplifier. So you can use FET as a separate, like a transistor as amplifier directly connecting to this. That itself consume less current compared to transistor, or you may use FET based op-amps. which consume nanoamps, microamps, or femtoamps, very low current, and it can amplify even microvolts, nanovolt signal without loading effect. That's why they will be using. Okay. So now that we talked about FET, correct? I just wanted to close the FET and we'll go to MOSFET. So we saw the input output characteristics of FET. Correct. This is input output characteristic of FET, and this is the amplifier circuit N-channel FET already told. By controlling the VGS, IDS can be controlled. This is the output, and this is how the FET amplifier works. The channel width varies. Correct. The channel width of FET varies when the gate voltage is increase or decrease. Because of that, output current is varying. So now, generally, when we talk about this one, gain.
So,
Right.
sir, basically the fine difference between the FET and transistor is that in transistor we control the output current by varying the IB, whereas
Base
here
current, base current. That's what we call as a current amplifier. Yes.
and here we are controlling by applying the voltage, right?
Yeah, gate voltage.
Okay, fine. Sir.
So apart from that, because why we are talking gate voltage, the FET doesn't take current. The current will be generally negligible. So whatever input voltage, there's no current flowing. So it avoids loading effect. And meanwhile, it can also amplify. If I vary this one, sensor signal, which is nothing connected. Sensor voltage connected is the gate voltage. Gate doesn't take current. So loading effect is avoided better than a transistor. But meanwhile, I want to amplify. My sensor signal, for example, thermocouple, all these things 0 to 100 millivolts, which represents 0 to 100 degree, or a force transistor 0 to 500 millivolts. Generally, sensor gives millivolts, represent 0 to, for example, 50 Newton meter. Torque transistor, force transistor 50 newtons. Those signals still millivolts, and if I connect to transistor, it will load and the error will happen. Instead of if I use a FET, FET doesn't take current, but still amplifies and provides a current. Finally, instead of IC, here we get ID, drain current. So amplification happens without loading effect. That is the main advantage of FET. Same thing in case of MOSFET, it input impedance is at least 3 to 4 times, or even so for example, the input impedance in case of FET may be megohms. In case of MOSFET, improved version of FET can be 100 megohm, 50 megohm, correct? 10 times, 50 times this one. So it doesn't take any current. Again, in MOSFET also, input is given to gate of the MOSFET, output is drain current. So the loading is virtually avoided if you use a MOSFET based amplifier. That's the advantage. Yeah. Anything? So generally when we say gain, yeah. Anytime when we say gain, we say output divided by input, correct? Output divided by input. In case of transistor amplifier, think about transistor. What we said, output is IC, input is IB in case of transistor amplifier, correct? So this is current, this is also current, right? Current will be unit level, dimension. We talk inside the amps. Get cancelled, the dimensionless quantity. Gain is a dimensionless quantity, correct? But in case of FET, my input is VGS, output is IDS, correct? Current in the numerator, in denominator you have voltage. So this is called as we know that voltage divided by current. What is it? Anybody? Voltage divided by current.
Resistance.
Ohm's law. What is Ohm's law?
Resistance, sir.
Yeah, fantastic. Resistance, correct? I have a metal bar. I connected a voltage. This is a metal, correct? So this is my V plus minus. So there's a current I. And that means the current I equal to V by R. This is Ohm's law, correct? So that means the resistor, the metal has a wire has a, or any element which is connected to what has a resistance. If it is a conductor, metals, the resistance will be very small, 0 or milliohms. If it is an insulator, R will be in the order of megohms or teraohms. Megohms or teraohms, theoretically it should be infinity, correct? If it is a superconductor, the resistance will be 0. All metals are good conductors. Generally, resistivity R equal to rho equal to very, very small. In case, correct? In case of insulator, rubber, wood, all those things, resist will be very high. Fine. Voltage divided by current is called as resistivity. Instead of that, current divided by voltage, correct? I divided by V is called as G. G is called as conductance. Electrical, very simple, correct? What is conductance? G is nothing but 1 by R, correct? We know R equal to V by R. So if I reverse it, sorry, V by I, extremely sorry, V by I. Instead of that, I by V I put, it is nothing but 1 by R. 1 by R is nothing but G. They are called conductance. Okay. So the gain of the transistor is called as beta, which is called as a current gain. Correct? Beta, if you see the transistor specification, they give VCC max, VB max, IC max, IB max, and beta, current gain. Right? Similarly, if I go to the market, if you want to buy a FET, there are more than 5,000 different type of FETs are there. The important parameters of the FET. Okay, so FET parameters. What are those things? VDSS max. We know that if I take my FET, this is gate, this is drain, this is source, this is symbol, this is a N-channel FET because in gate, the arrow is showing towards it. Okay, so I give a voltage. This is called as VGS, which is nothing but input voltage. And I connect second source is there, which is connected to the load resistor. And I connected to power supply, which is nothing but VDS. This is the source. This is drain, plus minus. This is a N-channel FET. Okay, so at bias like this, now there will be a current flow IDS. That is current flowing from power supply to the drain and comes back and circuits. And input is given here. Here, please note that this is called as IGS, will be close to 0 amps. Or IGS can be in the order of microamps or nanoamps, 10 power minus 6. So I can say that that's why we say it is called voltage control. I vary the voltage, which is can be your sensor. This is my sensor. Here, VGS nothing but input. Input can be a sensor voltage, correct? Sensor measures the parameter. So that needs to be amplified. So this is a FET amplifier. So the output is a IDS. So since FET parameters, what are the parameters? What is max effect? Take a FET. For example, I don't remember, I think BG something, BG 101 or something. Exactly, I don't know, long before. 30 years, we have never used it because nowadays. So it is a FET. I don't know, exactly, maybe wrong. The FET specification, if you see the data sheet like this, it will have BVGS max. For example, 30 volts. That means you can apply 0 to 30 volts here. This voltage can be 0 to now maximum this. That is called max. Next one is VGS max. Like VB max, VCC max, correct? This can be 0 to 10 volts. That means this voltage can vary from 0 to 10 volts only. Beyond that figure, the FET will destroy. Current will go the blown. Similarly, next parameter is IDS max. What is maximum this can go? 0 to, for example, 100 milliamps. Please note that there are FET which can take 0 to 10 amps, 0 to 20 amps. They are called power FET, correct? These are small signal FET. Similarly, it has what you call a GM. GM is nothing but transconductance. It is called as transconductance of the FET, which is nothing but gain of the FET. Transconductance is called a GM, which is nothing. Gain of the FET is called as, it can say 100 or 200, something like that. So that says that how many times the input output amplification. Input is a volts, output is a current, right? So that is measured in terms of transconductance, similar to beta, right? So here it is. So these are important parameters you have to remember. Okay. So again, before closing, I'll just take 2 minutes. I want to close the FET. Please see the very important figure. Okay, you can see here, similar to transistor amplifier, correct? If the input to VGS, correct? VGS is 0, correct? When VGS is 0, you can see that maximum drain current. Gate is fully open. Already told you, for understanding again, I am redrawing. We are giving a voltage between drain and source. There are two P this one. This is my gate. This is my drain and source. This is my VDSS plus minus. The current IDS will go. And now I need to give a voltage. Okay, I will get voltage being minus plus, correct? This is VGS. If it is a N-channel material, you have electrons. Here you have passed on holes. And I told you, when the VGS equal to 0 volts, my gate, there is a depletion region. Correct? Yesterday I told you, I will draw the depletion region for your understanding with different current color. This is my depletion region when VGS equal to 0 volts. Correct? So what is the gate width? Gate width is this width. Let me give color, you can see it. So this width, correct? This is the gate width. So I say that 100 micrometer for understanding, right? Now, if I increase my gate voltage to new voltage, again for understanding, again I'm giving some other color. So now my VGS equal to minus 1 volt. I given here minus 1 volt. This is 0 volt. This is 0 volt. This is minus 1 volt. What will happen? My depletion region will increase like this, bigger. This is very important. If you don't understand, you won't understand how the FET is working. Okay. Now, the whole area is non-conducting region. Now, you can see that compared to previous, when I give more negative voltage, the depletion region increase. But what is my channel width? My channel width is reduced compared to this. You can see that this is my channel width. It becomes smaller. So, my current reduces. So, you can see that when the VGS was this is the maximum current. For example, this is say 100 milliamps. Y-axis 0 to 100. So this is 50 milliamps. Correct. This is 75. Now I gave minus 1. Now you can see that it has reduced. So it will become, for example, 80 milliamps. So that means my channel will become narrow. The current which is flowing from this can go only the small area. Right. Previously bigger. So if I give more gate voltage, which they call a control. VGS is called a control voltage. Gate voltage is called control voltage. The control voltage coming from my sensor or whatever you want. If I give more sensor voltage, the width become lesser and lesser. So you can see that the IGS value is decreasing. Correct? Each time when more negative voltage, gate voltage become more negative in P channel, the width of the channel reduces. Correct? The non-conducting region, depletion region size increases, reduces a channel width. If channel width reduces, automatically current cannot do like a pipe. Bigger pipe, smaller pipe, smaller pipe. So the volume of water flowing to the pipe reduces. Same way, in case of FET, the width of the channel reduces, the current reduces. So the output current, IDS, is reduces. So if I increase, so by this, I am controlling the gain of my this one. So I am amplifying the signal. This is how it works. In the exam, you can expect the draw N-channel FET amplifier circuit. Okay. And explain how it works with this diagram. Yeah, like this diagram. Same thing will I shown here also. Okay, so this diagram is expected as you give. Again, I'm telling you, this is depletion region you have to show with the different voltage. Correct? This is for VGS equal to 0. So this should be minus. This is only one small thing correction. We make plus minus. This is my VGS. This is VDS plus minus. I give supply 10 volts. I vary is 0 to minus 4 volts or 5 volts. Okay. So this is for VGS equal to 0. Next thing what you will show? For example, next one, VGS equal to this. This much region, that is VGS equal to -1 volt. Instead of that, I say that VGS equal to minus, because you can show it. So this much region is to be blocked. Depletion region blocks the flow of electrons, correct? It is neutral. So my width becomes very small, correct? Very small. So this is for VGS equal to -2 volts. For example, 3 voltages, and then it works. Okay. So this is how it works. The next thing is, yeah, I wanted to close this. Gain we are talking about how the FET works, how the sensor can be. Again, this circuit also I showed how the sensor, this is my sensor. Sensor is connected to gate. Output voltage RDS is there. This is my IDS, and this is VDS. This one, this circuit also can be shown. Okay, you understand it? You got it? So before closing, I wanted to show the equation for the output. For example, output of FET amplifier is IDS. When input VGS is varied, can be calculated using IDSS. Note down this formula: 1 minus VGS divided by VP whole square. Okay, where IDS is called as drain to source current, which is nothing but output. Correct? This output is current. Okay, and IDSS is called as maximum. Okay, it is called as maximum saturation. Yes, there are two S's, correct? IDSS, maximum saturation current between drain and source. Okay, this value will be given. For example, if you are asked to compute the IDSS for different values of VGS. Okay, I say that VGS is varied from 0 to say 4 volts. Correct? So calculate IDS. Calculate IDS for 1 volt, 2 volt, and say 3 volts. And I can say the 0 to 3 volts is 3 steps. So what you will do in this formula, VGS will vary, VP will be constant. VP will be constant. The IDS will be given. In the problem, in your FET amplifier, the IDS, correct? IDS, maximum saturation current of the flowing between is given as, say, for example, 100 microamps. Correct? 100 into 10 power -6 is provided. VP is called a pinch off voltage. VP is called as pinch off voltage. For given FET, that value will be given. In the problem, I say pinch off voltage equal to 0.2 volts, 0.1 volts, something like that. These two values are given. Okay. Then you are supposed to calculate IDSS. Okay. IDS of calculate IDS for different values of VGS. VGS is input. If I vary this one, how this is output, how the output will compute. For example, draw a FET amplifier, common emitter, common source FET amplifier circuit. Correct? This is a common emitter FET amplifier circuit. Let me remove most of things so that you will see clear circuit. Okay. So this should be like this. Only small variation I will make it. Sorry. Being a N-channel FET, your input will be take down the circuit. This is plus, this is minus VGS. VGS varied from 0 to, for example, 4 to minus 4 volts. Because this is given, this is varied. So this is given as a gate terminal. So this is a N channel FET. Because the arrow is going in. If it is a P channel, the arrow will be coming out like this. Correct? So that you should note down. This can be connected. Both are connected. So this is the source, drain. This is called RD or load resistance, RL. The VDSS, for example, this I say 10 volts. Okay, whatever. So this is the circuit of the N channel common source. CS means common source amplifier. The common emitter amplifier. This is the circuit. Draw the common source FET amplifier circuit diagram. Explain is working, how the amplifier works. What you will show? You will show this diagram, and within that, applying different pinch of voltages, the channel changes. You can show it shades and how it works, and then you will be asked to calculate the parameters for different parameters. Compute the this correct IDSS. So you can expect some questions in some exam to understand it. Okay, now that we saw, I will go. Next one is called as what you call as MOSFET. Okay, MOSFET, it is exactly similar to your FET. Already previous we are talking for last 3 days almost. So this is called as VDS. That is drain. This is drain. This is the source, similar to FET. Only thing you can see difference is you have a P channel material, right? P material. So this is the semiconductor base material, right? For example, it is a cylindrical in shape, think like it is a cut section, right? So in which P channel made. So you can see the all are shown with plus symbol. That means these are positive holes. They represent each plus source holes, positive charges. This is a P material. That's what you know that. Okay. Then that is called as substrate. SS means subtrate. Correct. So there's a they take the gray color is a metal conductor. Metal is deposited over the P material, and so this is the connector. You can say that connector. So that is good. That is one thing. Okay, this is a P substrate. They call it a P substrate. That is called base material. In P base material, okay, they dope the region. Blue color is your N-type material. We already shown it doped. And one, you can see that in this, the N material doped this area, again this area, and this area. Right? Something like this, the doped like this. Remaining the left is as a P-type material. N is doped like this. Let me show it in red color, you'll understand. N is doped on. Okay, so one area which is bigger, correct? This is called a drain. They have taken a metal contact. The black color is called as a metal contact. You can see that this is nothing but wherever black is there, this one is the metal contact which is touching the N material. That is called as the drain, like a FET. Okay, then other N material, other end of the bar is again another this one, a big area N, that is called as a source. It is similar to your FET only. Junction field effect, there's no change. Slight change is there. Only thing is on P substrate, they doped the N material like this. And you can see that this is called as channel. This is called as channel. Channel area. Okay. So now channel area is connecting both drain and source. This is a continuous path. You can see that from the current. And what we have done, we have given a voltage, VDS. Okay. A positive voltage is connected to drain. Negative of that is connected to source, similar to FET. So literally it is same, correct? So because the drain and source are connected between the N material, it is called as N channel MOSFET. It is called as N-channel MOSFET. Slight constructional difference is there, you can understand. Okay, that's one thing. Then, in case of JFET, what did we saw? What we saw is JFET. You can see here. Directly, the P material is doped directly on the N material. That's why it forms a diode, correct? Physically, the N material touching with P material. So it forms a depletion region, form like a diode. I told you there are two diodes are there, correct? Both sensors. So in between you have the channel. And the channel is connected one end to drain, other end is source. Gate 2 is connected to P-type material. Voltage. Gate VGS is given to P-type material. Minus plus then my VGS. Okay, this is plus minus VDS. IDS current is going. This is output and input is VGS. Input is varied, so IDS varies. Correct? That's how the FET amplifier JFET works. In case of MOSFET, so only one thing is a small thin layer. Right? A small thin layer. Yeah. So you can see the violet color. This is called silicon dioxide. Right? So on the N channel material, they deposited a layer, a thin layer of silicon dioxide, which is an insulator. Silicon dioxide is pure insulator. Theoretically, it has infinite resistance. Practically, it has megohms or teraohms. Okay, high 10 power 9 ohms, something like that. Then on the insulator, above the insulator, you have metal deposition. Correct? So metal deposition, and which is connected to my VGS. VGS, we can say plus minus. This is input. This voltage can be varied. So 0 to 5 volts you can vary. Instead of directly connecting, please note that there is no junction forming between the gate and the drain channel. Like in case of here, I have an insulating layer on which I deposit a metal contact. This is metal contact and I given the voltage. So physically, if you see that between the N channel, this N channel and the gate input voltage, we are giving input voltage here. There's no electrical conductivity. Why? The silicon dioxide layer, which is insulated, prevents any current flowing inside this. That means IGS, which is called as a gate current. Correct? In case of JFET itself, gate current is very less. Why? We reverse bias it. Please note that we gave minus voltage to gate pin with respect to source. So these two diodes are reverse bias. Correct? So these two, we are giving minus voltage. This is minus, this is plus. Diode, this is anode. Anode is given with 0 volts, and the cathode side, which is an N channel, given with a positive voltage. Correct? This positive voltage. So because of that, the insulating layer, depletion layer, prevents the current going between these two, from N to P or P to N. Okay, that's how the field effect transform. If I give more negative voltage, the depletion layer increases, which reduces the channel width. And also gate current, IGS is also 0, because theoretically it's 0, but it will be in the order of nanoamps micros, because some leakage current is there between P and N, even in reverse bias diode. But at least there are possibility of current flowing. But in case of MOSFET, what we do, the construction itself different. You have an insulating layer. Above that, you are giving gate voltage, VGS. So that IGS cannot flow. Zero current, literally zero current. There's no leakage current also. Correct? So since the insulating layer has very high input impedance. So compared to the JFET in MOSFET. So because of that, this is called as a metal oxide semiconductor field effect transistor. Please note that it has a drain. It has a drain, it has a source, it has a gate, similar to the FET, JFET. But only thing is, it has additional one layer of silicon dioxide, which prevents gate current no gate current can flow inside. So in MOSFET, input impedance input impedance is very, very high because of the insulating layer. But still, now how it works, we'll see. Quickly, we'll see that we can store this one. With this, another 2 or 3 slides, we can stop it. And next class, we can start some other topic. Okay. Now, now we are giving plus minus. This is my VDS. Because of that, there's a current flowing IDS. That is the output, similar to the output. And this is my VGS supplied between gate and this one. So this is my input. If I vary the input voltage, you can see here, another thing is very important to note down. I told this is a pure metal, right? This is a pure metal. This is a metal. Okay. Metal, it is marked with a plus sign. Right? So if I connect a positive terminal of the VGS, this is my positive, negative is connected to drain. Correct? This is 0 volts. This I am varying 0 to 5 volts. Gate voltage can vary. So if I give 1 volt, some positive charges, correct? Beginning with the positive charges are deposited in the metal contact. Okay? Because the positive voltage applying at VGS, if I apply 1 volt, for example, there are 10 positive charges coming and sits on the metal contact. Please note that it cannot go inside. It can just sit there and store there. In the gate metal contact, because of the positive voltage, instead of 0, I give 1 volt, there are 10 positive charges are sitting here. Okay. What that will do is it will attract the negative charge here. You can see here. Maybe it's a green color, you'll see here. Equal number of electrons. What is the N material has? It has electrons. Correct? It has electrons. So those electrons which were spread here randomly will be attracted and come and deposit near the insulating layer. Correct? So now, if you know that if electrons are there, these electrons can move from here to here. And okay, so we say that the collected electrons from the N material, which was dispersed randomly, will be attracted below the gate terminal here. Okay, as I told you here. Maybe I can make it a red color or some other color, you will see that. Okay, in the N material, this one, when come on this one, it forms a layer. Correct? This is called a conducting layer. This is called as conducting layer. Conducting layer means nothing but attracted electrons. Conducting layers. That happens if I give a positive voltage this. If I give 0 volts, VGS equals 0 volts, what will happen is, let me clear it once again. If I give 0 volts, correct? This is 0, VGS equals 0, the electrons will be randomly be there. Now, if I give 1 volt, positive charges are attracted. For example, 10 particles, 10 number of electrons will come and sit here. Instead of that, if I give VGS equal to 22 volts, 20 positive charges will come and deposit here. So 20 electrons will come and think it. So if I give VGS equal to 3 volts, more electrons will come and get deposited. 30 electrons. So more current can flow. That means if I vary my VGS from 0 to 5 volts, the electrons which were dispersed inside the N material will come and get deposited. So there will be a current flow will happen between these two terminals. So the IDS flows. This is how the MOSFET works. Okay. So it is similar to the FET, JFET, but only thing is it has an insulating layer which provides very high input impedance, correct? So that means the gate current is almost 0. Gate current is approximately 0 amps or in the order of nanoamps per pico. Input impedance can be in the order of 10 power 7 or 10 power 8, even 10 power 9 ohms. Right? In the order of 10 mega ohm, 20 mega ohm is one. That is MOSFET. So it is much better than the FET. FET itself doesn't take current. By controlling input voltage, the output IDS is varied. That is much better than transistor amplifier because base current is taken and loading effect comes. Instead of FET, if I use MOSFET as an amplifier, correct? MOSFET as an amplifier, what will happen is it provides much better input impedance, no loading effect, and the output current, IDS is the output current, is VGS the input. If I vary the input, the output is varied by controlling this. Because so the advantage, you understood? Any questions? So no problem. So again, in the previous class I showed you symbolic representative of N channel JFET. This is JFET. Correct? This is again JFET P channel. P channel. Same thing in case of MOSFET also, you have N channel type, P channel type. Okay. What is the difference? I will just tell one thing, quickly note down. This material is N type N material. N-type material, and these materials, the whole area will be P material. Okay, and you have the metal gate with insulator. All these things, the only thing interchanging. N material will be here, N material base material, channel will be made with the P material. And if you can have the VDS and this one, all those things, it is called a P channel MOSFET. What is the difference? The current carrying conductors, current carrying particles. I can say that particles are holes, which are nothing but positive charges. Correct? P-type material has positive charges. Here, instead of this, we have P-type material. This will be N-type material. Then it is called as P-channel MOSFET. Right? So, only difference. Otherwise, functionally, N-channel, P-channel working same. But some difference is there. Please note that one small thing, what is the advantage, whether which one to use for understanding purpose. N-channel material has electrons as current carriers. In N channel or N type material, electrons are current carrying particles. Current is carried because of movement of electrons. And in case of P channel, whether P channel MOSFET or P channel JFET or PNP transistor, correct? We call majority carriers. Majority carriers in N material or N channel material electrons, which is responsible current flow. In case of P channel or P material, the majority carriers are holes. Majority carriers are holes, which are called as positive charges. Okay? Okay. Both are same. Slight difference. The electron, what is the electron mass? Any idea? Electron mass of individual electron. Okay, mass of individual electron is much smaller than mass of hole, positive charge. So, if mass is less, electron can move faster. The speed of the electrons in superconductors, correct? In superconductor, zero resistivity in superconductor, the speed of the electron is 3 into 10 power 6 kilometer. Sir, okay, 3 lakh kilometer or 3 into 10 power 8 meters. Okay. In case of the holes, the speed will be some 2 times lesser, approximately exact number, it will be lesser. So if I make a circuit with P channel material or P type P channel FET or P channel MOSFET or PNP transistor, the working frequency, what is maximum frequency it can work will be lesser. Working frequency of P channel will be lesser than N channel FET. Okay. Because of that, if you see your microprocessor, for example, i6 processor, i7 processor, i10 processor, or any microprocessor in your cell phone, laptop, supercomputer will be made with N channel MOSFET. It will be made with N channel MOSFET because they can work at a higher frequency. Higher the frequency, the speed of computation will be better. Calculation will be better. That's why nowadays P channel MOSFETs, we say that two type of MOSFETs are there. N channel MOSFET, symbolically represented like this. This is P channel. These were earlier used. For example, first microprocessor. The word microprocessor was microprocessor itself was invented by Intel company. Intel company started with this one. They call i4004 microprocessor in 1978-74. They started, three people together started the Intel company, which now you have all your desktop computer, all this thing. Yes, i7, i10 processors. 1970, the first microprocessor was i4004. It is called a 4-bit microprocessor. Okay. Then they invented 8080. It is a 8-bit microprocessor. I have used this when I was a BTech student, 1982 programming. Then came 8085 microprocessor. You would have studied. Right? It is 8-bit. All this process, this early processor were using PMOSFETs. 8080 and 4004. All this one using PMOSFETs. Okay. I am talking 1970s and 80s beginning. Subsequently, 8085, so they were start using N-channel MOSFETs. Right? Inside your microprocessor, i7, i10, you have 20 million, 30 million, 40 million N-channel MOSFETs packed in few cubic inch or less than a cubic inch volume. Right? 20 million MOSFETs, N-channel MOSFETs, but early microprocessor they are using, but they have to do. But sometimes you may have power MOSFETs available for this. Okay. Now that you understood what is a MOSFET, how it works, otherwise both are similar. So I will stop here. Monday we will start with only one thing is pending. Yes,
Tuesday,
please.
sir. Tuesday, sir.
Yeah, Monday is holiday. Okay. Tuesday we will start at another power. Last one, which I wanted to cover is IGBT. It is a part. So the one small thing I want to do, MOSFETs are available. Current rating again. Okay. Just before closing, I wanted to talk few lines. Okay. MOSFET specification again talks about VDSS max. This is available. MOSFETs are available rating from 30 volts to even 5000 volts. Correct? If any voltage, I told you, if the VDS, the drain to source voltage is more than 100 volts, they are called a power MOSFETs. Okay. Then IDS max can be 1 amps. Correct? 1 amps to even 500 amps are, there are very special case, easily 50 to 100 amps current. Right? These MOSFETs having higher voltage, 100 volt, 200 volt, 500 volts, and current rating 20 amps, 30 amps, 100 amps. They are all called as power MOSFETs. Power MOSFETs. They are used in driving the motors, electric motors. Whether we talk a BLDC motor or an induction motor or a permanent synchronous motor used in an electric hybrid vehicle. The lithium, as I told you, I have my motor. This is my motor, and this needs to be driven by a power amplifier circuit. Power amplifier can be MOSFET. Many times now they are using MOSFET or power transistors, and this is going to drive. Correct. This is the motor. The motor may be working at 600 volts, say 500 amps current or 400 amps current. Correct. So the power is multiplied by these two. 100 amps, at least you say the 100 or 50, whatever, depending power rating. So, and they need voltage around 600. Who is supplying? From your lithium ion battery pack. This is lithium ion battery pack will be powering this power amplifier. Okay. And you have your vehicle controller, which gets throttle input. Correct. It measures vehicle speed, all those things. It generates control signal and gives this is control signal. When the driver presses accelerator pedal, correct. So 0 to 10 volts. Your TPS sensor gives 0 to 10 volts because of the controller generates 0 to 10 volts control voltage and supplies to the power on or 0 to 100 volts voltage input to the, for example, VGS, gate voltage, correct? The gate voltage generated by the controller. Okay, VGS. Because of that, it generates IDS, the my power amplifier. That is supplying the current. So this is how the power amplifier. This can be MOSFET or power transistor, or it can be SCR. Correct? Where the SCR will be used? What type of motor you will be using SCR? Yesterday only we talked.
Sir, induction motor
Induction motor,
and
or
DC
it can
motor.
be DC motor also.
DC motor. Yes.
Also, if it is a MOSFET, correct, it can be used only for BLDC motor or DC motors. Okay, power amplifier also can be generally used for driving BLDC motor. Nobody is using this one or permanent by this, but permanent PMSM synchronous motor. If it is induction motor, you will be using SCR, power SCR. Power SCR means they can handle higher voltage, 400 volt, 500. Who is supplying voltage? Lithium ion battery pack of your car. Correct? 400 volt, 600 volt battery pack. That voltage will be given to the power MOSFET or power transistor or SCR circuit. And then the control signal generated by vehicle controller, which using LiDAR, radar, all those things are external direction. Apart from autonomous vehicle, which this in case of manual vehicle, IDAS means driver is pressing the throttle pedal. That signal TPS sensor is given to your vehicle controller, which in turns comes to your motor. If it's an electric vehicle, EV. Otherwise, the controller hybrid vehicle means the vehicle controller will control engine as well as this will be electric motor, EM control. Similarly, the controller will be controlling engine, IC engine also. Fuel injection. Already we saw that. Correct? Maybe port fuel injection in case of petrol or GDI, or in case of CRDA in case of diesel engine. Your hybrid vehicle may use diesel engine or petrol engine and also electric motor. If you pure electric, this is what the configuration. I stop here. If you have any doubts, we can talk. Otherwise, we'll see you on Tuesday. We will see only on the IGBT, which is the, if you want, I can close today also. Is it okay? Just to, otherwise, okay, we'll talk at this. Already you have 1.5 hours. No issue, additional hours. So we'll stop here. Tuesday we'll start, but next week also we have 2 hours. Thursday we'll have, because we have missed more 4 classes. We have to compensate. Okay.
Okay, sir. No problem.
Excuse me?
Sir, no problem, sir. Next week we will take it, sir.
Okay. Okay. So see you on Tuesday. Enjoy your weekend. Okay. Holiday also. What are the holiday? Monday?
Sir, Monday holiday.
Okay, fine. Anyhow, long weekend. Enjoy. I know that in fact.